Hello students, welcome to this online course of Strength of Materials. So in the previous lecture we have studied about the temperature stresses. So let us move forward and try to solve some more problems related to temperature stresses. So our next problem is stating a steel rod 20 mm diameter and 1.5 meter long is constrained between supports A and B, as you can see in the diagram also. The material is stress free at 27 degrees Celsius. Determine the stress in the material when the temperature increases to 50 degrees Celsius, if the supports are unyielding and if the support B yields by 0.1 mm. E and alpha is given for the material, that is for steel. So in the previous lecture, the first part is same as in the previous lecture we have solved. Like, we are trying to raise the temperature. After raising the temperature, the material will try to expand, but due to rigid supports or unyielding supports, this body will not be able to expand. So due to this expansion, the stress will generate because we are restraining that expansion. But what is the second part? In second part it is saying if the support B yields by 0.1 mm, that means 0.1 up to 0.1 mm of expansion there will be no stress. So support B can take the deformation of 0.1 mm. So first we have to check how much is the expansion due to this temperature rise. So what is your delta T here? Let us check. It will be 23 degrees Celsius. So first part is when the supports are unyielding. So what we can do, we will assume that this support is not here, so we will let it expand by delta L. Okay, but due to this expansion, because this expansion is not there, so some stress will be acting, which due to which it has not expanded. So first we have to calculate the length by which it will try to expand. So L into alpha into delta T. So it is coming out to be 0.414 mm. So this corresponding to this deformation, the stress will generate. Now the cross section area, you can solve it by pi by 4 d square. So the compressive force required to bring the material to its original length can be found out from this equation, or simply you will put P by S sigma also, directly you can get stress. So either find the force first, or you can find directly the this stress also. So force is coming out to be 17,341 Newton or 17.34 kilonewton divided by area will give you the stress generated due to this kind of deformation when supports are unyielding. But now in the second portion, what it is saying, this is 0.414. okay, here it is point. Now 0.1 mm is allowed as yielding of the support. So now this difference, like that is 0.314 mm, will be resulting in the stress. So let us see how we are going to do that. When the support B yields by 0.1 mm, the bar will be unstressed up to 0.1 mm. So stress will come into picture after the point B has yielded 0.1 mm. So the change in length will be now 0.414 minus 0.1, that is 0.314. So in this case, as you can see, if due to less deformation, less stress has been generated. In the previous case it was more than 50, now it is 41.86 only. So this was the case of yielding and non-yielding of supports, unyielding and yielding supports. Now let us see our next problem. It is a composite bar of like various cross section, and materials are also different. A composite bar made up of copper, steel and brass is rigidly attached to the end supports as shown. So ends are fixed. It is not be able to move if we are going to raise the temperature. Determine the stresses in the portion of the bar when the temperature of the composite system is raised by 70 degrees Celsius if the supports are rigid. So let us say presently temperature is 30 degrees Celsius. So it has been raised to 100 degree because the whole temperature has been raised by 70 degree Celsius. Okay, so delta T is directly given to us. Delta T is 70 degree Celsius. Now one more thing, like there is no external load, so every portion will be having the same force. So P generated, P for copper, P for steel, and P for brass. This all will be same. Only stress will change because the area of cross section is not same. So that means if stress in brass is sigma B into AB will be equal to stress in copper into area of copper will be equal to stress in steel and area of steel. So this equation is valid here. Also, the second equation can be net deformation. Delta is 0. Calculate individual deformation, and finally we will put that value to 0. Clear? So this is how we are going to proceed with this problem. So first thing we have to check whether the ends are fixed or not. So ends are fixed, so delta will be 0. Also there is no external load, so the load will be same but the stresses will be different due to different areas, cross section areas. So these are some properties like which is going to be used in the question. So copper EC is given, alpha C is given, steel E is given, alpha is given, and brass E is given and alpha is given. So as you can see, brass will expand most due to its alpha, and after that copper, and then it's steel. So let us see how we are going to do that. So first thing, we have calculated the area of each of the material, cross section area of each of the material. So copper it is 50 mm, so pi by 4 50 square, so it is coming out to be 625 pi. Steel it is 400 pi, and for brass it is 60 mm, so 900 pi. So this is the respective areas. Now when the temperature is raised, each portion tends to elongate, which is resisted by the rigid supports, and the compressive stresses are developed in each portion. However, the forces in each portion will be equal. And one more thing, why compressive stresses are generated? Because every portion will be expanded only, okay, but due to the rigidity of the supports, they are not be allowed to expand. So every portion will get the compressive stress. So this equation, as I have told you, this is valid here. So we can what we will try to do, we will summarize, like we will express two of the variables into one of the variable. So let us say sigma B we are fixing, okay. So what we will do, we will express sigma C in terms of sigma B and sigma S in terms of sigma B. So if you are taking first and third, then you will be getting this equation, and if you are taking first and second, then you will be getting this equation. So sigma C is coming out to be 1.44 sigma B, and sigma S is coming out to be 2.25 sigma B. So this is the first relation we have got. Now let us check what is the deformation. So deformation, if the supports are not there, one of the support is not there, so the body is free to expand. So it will expand by this amount, alpha L into T, for all the three materials. So after putting all the values, we are getting 1.106. okay, this is 1.106. so this is the total elongation, but this is not being allowed. So this will be registered by what, this will be registered by the compressive stresses generated. So due to support, the elongation is prevented and the stresses are developed in the material. So what we are going to do, we will check how it is coming to be 0, because the compressive forces are there which are resulting in your what, compressive stresses. So this is sigma C, LC, EC, this is sigma S, and this is for steel. So there will be S everywhere, and this is for B, brass, okay. So finally you can see here, like this is sigma C, this is sigma S, and this is sigma B. After putting all the values, we are getting final equation in terms of sigma b only. Okay, so sigma b is calculated as 84.95 MPa, and by the relation of sigma c and sigma s to sigma b, you can calculate all the stresses here. So this was also not that tough, but just you have to be sure, like first you have to express all the stresses in one material, and then you have to just put all the deformation due to compressive stresses to the net elongation due to temperature rise. Okay, so in this way you can solve these type of problems. One thing is, you have to be sure, like force is same, stresses can be different, but due to absence of any external force, the force in each member will be same, then only it will be in equilibrium. So that equation is also valid here. Now let us see like some different type of problems. If a steel tube of 35 mm outer diameter and 30 mm inner diameter encloses a gunmetal rod of 25 mm diameter. So gunmetal is nothing but the copper only, some different form of copper. So and is rigidly joined at each end. If at a temperature of 40 degrees Celsius there is no longitudinal stress, determine the stresses developed in the rod and the tube when the temperature of the assembly is raised to 240 degrees Celsius. Also find the increase in length if the original length of the assembly is 1 meter. So let me just show you what is going to happen actually. So this is your initial condition. Okay, so gunmetal is there and it is being encased by, initially it is of same length. Okay, so this is your gunmetal enclosed by steel, this is steel and this is gunmetal. Now if the temperature is being raised, so let us see, this is your fixed support. So due to different alpha, this is steel, alpha c is greater than alpha s. That means if length is same, temperature rise is same, then delta L of copper will be greater than delta L of steel. So copper will expand more and steel will expand less as compared to each other. What does this mean? This means like if this rigidity is not there, okay, so gunmetal is going to expand more, it can be any value, and steel will come here, somewhere here. But this is not going to happen, they are rigidly connected. So what will happen, they will compromise and they will attain some in between position. Let's say this is here, so finally they will be like this. That means the gunmetal was compressed and the steel was stressed, expanded. Okay, whatever was like due to temperature after deformation, they will have to achieve like some common point due to compatibility. It is not possible that gunmetal will expand more than steel because they have rigidly been joined at the ends. So that means the copper, the material which is having a more alpha will be in compression, and the material which is having lesser of alpha as compared to the other material, that material will be in tension. So here steel will be in tension and copper will be in compression. So let us see how we are going to solve this problem. So this gunmetal properties are there and we have calculated the area also. So area of gunmetal and area of steel. So here you can see the stresses will be different, so that is different. So let us see what point I am trying to make here. As the coefficient of expansion of the gunmetal is more as compared to the steel, the final expansion will be less than the free expansion of gunmetal due to temperature rise, and thus compressive stresses will be developed in gunmetal. As I have told you, they will like compromise at some in between position, because gunmetal would have tried to expand till here and steel would have tried to expand till here. So in between they will compromise, and they will, like, the steel will be in tension and the copper will be in compression. In a similar way, as the coefficient of expansion of steel is less, the final expansion will be more than the free expansion of steel due to temperature rise. So this, whatever I have told you, just I have tried to summarize here. Now what will be the compatibility equation? So deformation due to temperature rise will be there. Now the point is, due to temperature stresses, what is going to happen? So the deformation due to temperature rise plus, because steel is in tension, so deformation due to tensile stress in steel, this side we have taken steel and this side copper, will be equal to how much? Deformation due to temperature rise minus deformation due to compressive stresses. Okay, for like the copper was about to reach here, but due to this compressive stress it has come up here. So deformation in both will be same. So in steel we have to add the deformation due to tensile stresses, and in copper we have to subtract it. So this is your final compatibility equation. Alpha s delta t ls plus like strain due to stress, that is sigma s by es multiplied by the length, that is ls, will be equal to alpha c delta t lc, and minus your minus, because the stress is compressive. Once you have reached to this equation, then your problem has become very easy. This is the main concept here, that the deformation in both will be same, but how they are coming same, this is the concept here. Now just because lc, length of copper and length of steel is same, so l will get cancelled out, and finally you are having this kind of equation. Like this you can directly use if the marks allotted to the question is less. So this is your final equation. Put all the values and finally we will be getting P, because again due to equilibrium force will be same, the area the stresses can be different but force is same. So P is there, area is there, so we can get the stress in steel, it is coming out to be 132.56, and stress in copper is coming out to be 68.93. Now the second part was to calculate the increase in length. So increase in length is both, this also will give the same value, this also will give the same value. So this is your homework. I have calculated from steel. Check whether from like this copper also it is coming out to be 2.847 or not. So this you have to check and tell me whether I was telling the correct or not. So this is all for today. In the next lecture we will try to solve some more problems, and in this week or in like next week this chapter will be over. So this was today's lecture. Thank you.